Hello everyone, this is the sixth video of digital signal processing. Today the subject is sampling, and we have two videos, part 1 and part 2. In part 1 I will inform you about the sampling and the relation between Fourier transform and discrete time Fourier transform. For example, we have a band limited signal xt, and here is fs is the sampling frequency, and xn is the sampled signal, which equals xn t and is integer here. T is the frequency period, and xst is the sampled version of the continuous time signal. We obtained the sampled signal by sampling, which is the multiplication of xt and the impulse train. And the impulse train, as you can see here, is the time shift version of the delta functions. Here xst is the xt times delta t minus nt, and in frequency domain the multiplication becomes convolution, and therefore the frequency Fourier transform of xs is the convolution of x continuous time signals Fourier transform and the convolution of the impulse train spectrum. And the impulse train spectrum, or the Fourier transform of impulse train, is also the impulse trains. As you can see here, the convolution between x and the delta function is the frequency shift of x. As you can see here, for example, we have a spectrum, band limited, and the maximum frequency is capital B, as you can see here, and this is the impulse train spectrum, is also an impulse train. Omega s to omega s3 omega s is the in radian over second frequency. Here the convolution of these two functions is the frequency shift of x, as you can see. And we generally design filter in discrete time Fourier transform and Z transform, but here this is in the Fourier transform. Therefore we need a relation or transformation between discrete time Fourier transform and Fourier transform, and capital omega, as we can use here the transformation variable of Fourier transform, and small omega or w is for discrete time Fourier transform variable, and w equals omega t is the transform between discrete time Fourier transform and Fourier transform. For example, here we have the spectrum of sampled signal as above, and for example b here is 2 pi over 3t, and if we want to transform the spectrum into discrete time Fourier transform, we use w equals omega t, and if we put 2 pi over 3t to omega here, we get 2 pi over 3 here, and this is in discrete time Fourier transform. If we design a low-pass filter in discrete time Fourier transform, such as the spectrum here, it's a low-pass filter, and the cutoff frequency is pi over 2, as you can see, and the output of the filter is the multiplication of these two spectrums, and the output here 2 pi over 3 is greater than pi over 2, as you know, and the multiplication here we get this shape for every 2 pi here. And if we design a low-pass filter, for example, in Fourier transform this time, and we determine the cutoff frequency as 500 Hertz, and let sampling frequency is 2 kilohertz, and let's change the variable to radian over second here by multiplying 2 pi. We get his, and the low-pass filter, the ideal low-pass filter shape is like this, and this is 1000 pi, and this is minus 1000 pi here. And if we change the variable from Fourier transform to discrete time Fourier transform using this formula here, as you can see, and we get pi over 2 for the cutoff frequency in discrete time Fourier transform, and the output is also as the same, the input signal spectrum times the filter spectrum, and we get the same result.